Hey, let's start. So we need to finish on relative motion, the Cauchy-Wilshire equations, and how you actually connect the initial conditions for those with what happens in reality between the two spacecraft, and how you compare them with what really happens between the two spacecraft. How good are they of an approximation? When do they start breaking apart and not really approximating reality well? So we'll discuss that. I will show you what is your homework, uncollected homework number 9, I believe, that I posted today. So between that and 7, that's basically your homework 3. I cannot tell you more than that, really. I mean, I'm just telling you what I'm going to give you. So if you haven't done them, again, it's on you. It's your choice. But that what prepares you for homework 3 and the test, of course, as usual. The test, as usual, will be probably 10 questions, conceptual questions, maybe a few calculations, not crazy calculations. I can't ask you to do that in 50 minutes, unless you guys want the final, which is 3 hours long, which you probably don't want, right? So one thing I wanted to tell you, I sent you an email. The end of semester evaluations are open Saturday. They go until the 22nd. I do not see anything until May 5th, probably. So don't worry about your input affecting what I'm going to put in the test. That doesn't happen, okay? But do take the time to do them, because some classes have a response of like 10%, and that's really pointless. If I have 100 people and only 10 respond, that is not a good statistics. So I will definitely remind you until the 22nd to do it. Some people even spend time to have students doing it in class. I don't want to do that. I think you can do it by yourself. It takes maybe 2 minutes. So before I move on, are there any questions of what we've done so far? Yes? For last weekend, we're going to be in that same room. Yeah. Oh, yeah. At least that's what I have it booked. Yeah, shouldn't change. Okay. So any ideas on basically how to find Cauchy-Wilshire initial conditions? Because what I gave you last time, I gave you the code, is just some randomly created x0, y0, z0, and their time derivatives. I just made them up. I mean, maybe with some experience you can guess reasonable numbers that make some sense, but we haven't done that. I just created those numbers and simulated the motion. But reality is that you have two objects flying on their own orbits. We called one the chief, right? And the LVLH is defined with the vectors that have to do with the chief's orbit, which he approximated as circular, and the other one is the deputy. And these x, y, and z have to do with the vector that connects the two, chief and deputy, right? So this is the position of the deputy with respect to the chief, and this is the velocity of the deputy with respect to the chief. It's so relative position, relative velocity. So how do I figure them out, starting from knowing the absolute trajectories of RC and RD? In other words, if I have at a certain time RC 0, right? And the velocity of the chaser is 0, and the velocity and position of the target at time 0. Sorry, changing nomenclature here. Deputy. Chief and deputy. So if I have these, how do I go here? What is the connection between these? I don't know. Because that's really what you want to do. You choose your ISS as the reference point. You know its orbit. You will probably be able to measure a certain position and velocity of the deputy. If you want to switch to using Cauchy-Wilshire equations because they are convenient, well, how do you find these numbers? Any ideas? It is basic. I was going to say dynamics is really just kinematics. It is really just kinematics. So let's start from the vector itself. What I want to find is rho at time 0. And it's really valid for any time. I'm just focusing on a specific time. But I put the 0 here, but I can also remove it. This is valid for any particular time. So I want to figure out this guy, and this guy, having this information. Someone gets me started here, maybe? Again, this is just basic dynamics. Forget about that these are spacecraft. This is a point mass. with the position and the velocity. This is another point mass with the position and the velocity. And I defined the LVLH. Maybe I should refresh what that is. The I of, I'm going to have a lot of symbols here. Let's see. I of LVLH was, again, R of the chief over its norm. Remember? The K of LVLH was in the direction of its angular momentum, right? And then J is the cross product of the two. So that vector is expressed in this basis, right? These I, are you fine with me just having an L here by, assuming that's LVLH, so I don't have to write it all the time, and you don't have to do it either, as long as you remember. So the other one would be an E, probably, ECI, because I have to work with that basis as well, okay? So I'm going to have L for LVLH. I'll write it here. L indicates LVLH, and E is going to indicate ECI. How about that? It's going to be easier. But the point is I need to find the projections of this vector in the basis. Well, what is that vector? Rho. Let me drop the 0, because, again, this is really valid at any time. Rho is the radius of the deputy, the position of the deputy, minus the position of the chief. Any concerns? No? Now, these two guys will most likely be expressed in ECI, in a basis fixed with ECI, right? So I need to do something here. What do I need to do? No. Not really. So, in other words, this is probably given to me as, a big X, I of ECI now, a big Y, J of ECI, and a big Z, capital Z, K of ECI, right? It's just that this vector is most likely given what you've done so far, integrating ODE 45, the equations of motion, you've done it in ECI, right? And so at any given time, doesn't matter if you do it at a time that you call 0, or any given time, this is true, but most likely you will have these in MATLAB. In other words, you will have 3 numbers, and those 3 numbers are this X, this Y, and this Z. Those are the projections of Rho in a basis which is not the one you want. So you just have to transform the basis, right? Okay, this is really nothing new. It shouldn't be. The basis I, J, and K of LVLH, well, it's already expressed. Those little 3 vectors, unit vectors, are already, once you do this operation, they are already expressed in ECI. Because RC is in ECI, HC will be in ECI, and this is the cross product. So you will be able to say that these 3 vectors project into these other 3 vectors. Again, they're all unit vectors. And there is a 3 by 3 matrix in between. I don't even want to call them other than A, B, C, F, G, H, and I. 9 numbers. Right? Do you agree on that? I'll actually open my MATLAB file, which will have to be your uncollected homework, and show you what this means. It's just that you're given a position of the chaser. It's a vector. Not the chaser, it's the chief. Of the chief, it's a vector. Normalize it. You get these 3 numbers. That's what you get. You do this operation, compute the angular momentum of the chief, normalize it, you get these 3 numbers, D, E, and F. That's what MATLAB is going to create, right? Make sense? Because you're given those vectors in ECI. So I had a question at some point. Why is this? So let me call this matrix, I'm going to call it R, for example. But it's also called sometimes the direction cosine matrix, which you must have seen in other classes. But it's called direction cosine matrix because these elements in the matrix are actually the cosines of the angles that are formed between these, among these unit vectors. If I sketch here the basis for ECI, this is IE, JE, KE. And then I have some weird orientation, LVLH, IL, KL, and JL, right? So let's focus on what happens between the two I vectors. You can always define an angle between the two, right? Call it alpha. The dot product between IE and IL is the cosine of alpha, because these are unit vectors. And what is the dot product between IE and IL? Here it is. You see that? So that is the cosine of alpha. And the same goes with every combination here. So all these numbers are actually cosine of all the angles that you can imagine between any of the unit vectors of the basis and LVLH and any of the other unit vectors. So I will form another angle with JE that you can call beta, and another angle with the KE that you can call gamma. And so you populate that matrix with those cosines. That's why it's called direction cosine matrix. Okay, anyways, I have that basis. I don't think I need this anymore. Do you want me to show you how you transform that vector law? No? Should I just jump to the conclusion? If I give you, huh? I can show you? Okay, thank you. Yes. Well, you just substitute, right? So let's see. You start from this, but I have the vector expressed in this basis, so I will have to invert this matrix. The property of this matrix is, of the direction cosine matrix, is that the inverse is also the transpose. We don't need to justify that. It's a known fact. So what you can write, I'm going to keep using A, B, C, and D because that will show it pretty clearly. So you basically take that matrix and transpose it. D, E, F, G, H, I. Okay, this is an E. And here I will have these guys. Now I can take these unit vectors and substitute where I see them in rho. So rho is going to be equal. We need to be careful here. Capital X, IE is AIL plus BJL plus, I'm sorry, not B, D, right. It's the inverse, which is also equivalent to the transpose, so you can take that matrix and transpose it. A rotation, what you guys call rotation matrices, you can do that. No, it doesn't. Does it? No, take the first row and it becomes the first column. Take the second row, it becomes the second column. Make sense? That's what you do when you transpose. No, I mean, they're letters. I was doing the same here. I was doing B again, but that's a D actually. Plus G, what, K. L plus, okay, then same thing with Y, but I have B, I, L plus E, J, L plus H, K, L plus, last one, Z. Here I have C, I, L plus F, J, L plus I, K, L. And I'm going to reorganize this. Collecting all the I's, the J's, and the K's. Let's see. What is multiplying IL? I have X, A plus Y. These are all capital X and Y's, right? And Z. B plus capital Z, C, and this is on IL, right? Plus, I know this is tough stuff. X, D. Now this is a good exercise. You know, you don't believe this. I do it every time I have to transform a vector between bases. If I'm not sure what I'm doing, I redo this. Because you take that matrix and you don't use it in the right order, you're not gonna, what you get doesn't make any sense. So, where was I? XDYE plus ZF on JL plus XG plus Y H plus Z I K L. Okay. Another way to write this, going back to matrices, is the following. And column and row vectors is doing this. I just put I, J, and K now in a, instead of a column vector, I put it as a row vector. MATLAB speaking MATLAB language here. And here I have what? I have A, B, C, D, E, F, G, H, and I again. So I basically have I. So all this just to prove that you start from this, right? Because as you subtract, if you just take the vector R of the deputy and the chief, again, what that is capital X, I-E plus capital Y, J-E plus capital Z, K-E. This is R deputy minus R chief, right? So you start from knowing this. Well, find that rotation matrix. Basically, that rotation matrix is the components. Remember, this is I, this is J, and this is K of LVLH. So you take these and multiply that matrix in front of these components. So in other words, little x, little y, and little z are that matrix R times the components in ECI. It's really not a big surprise. Yes? The chief is the reference satellite, which is on circular orbit, and is just sitting on that circular orbit forever. It's the point of linearization to find the Cauchy-Wilshire equations. The deputy is another spacecraft that is close to it. Depends on what close means for the particular problem, but it may not be in circular orbit, but it needs to be close. And I'll show you a couple of plots about when, to show how these equations, they start failing as you go far away from the chief. Okay, so basically that's how you find your initial condition for Cauchy-Wilshire equations with x, y, and z, right? Again, if you are given a position vector for the two at some initial time, a time that you call 0, then it means that you're given these three numbers, compute the LVLH basis as we have done and I have erased, will give you the matrix R. That's your initial conditions for position. Okay? Questions? We're missing the velocity, right? Can I take this off? Yeah. Okay. Now we use the transport theorem. It's always there, hiding behind something else. So if I go again from this, rho is my position of the deputy minus position of the chief. How about I take the rate of change of both sides with respect to the inertial observer, which is ECI. That means since rho now is expressed in LVLH, I want to do that. I can write this. The rate of change of rho respect to t in LVLH plus the angular velocity of LVLH with respect to ECI cross with rho itself, right? This is transport theorem. These two pieces together, they give you how rho is changing with respect to the inertial observer. Remember? ECI, transport theorem, nothing special. And then these two, let's just directly say that we take the rate of change of them in ECI. So that gives me the velocity of the deputy, and this gives me the velocity of the chief, right? Okay. What is this? This is what I want. This is how the LVLH observer, you sitting on the International Space Station, you're hugging this XYZ axis, you're attached to them. That's how you see the position vector that goes to the other spacecraft changing. So in other words, this vector is x dot I of LVLH plus y dot j of LVLH plus z dot k of LVLH, and these are the things that I want to find. Those are the pieces of information that I'm missing to give some initial conditions for CW. Okay. And again, this is valid. I removed the 0 at this point, as you can see. What I'm doing is valid at any time. So in other words, that procedure finds the x, y, and z in LVLH at time 0 or any other time. This is going to find the x, y, and z dot, where x, y, and z are coordinates in LVLH at any time. And that's exactly what the software is going to show you. And that's the homework that you have to complete. Okay. Well, then I'm basically done here. Really, I just have to move stuff on the other side. So my x dot I plus y dot j, this is LVLH, plus z dot k LVLH is VD E minus V chief E minus omega L with respect to E, bless you, cross with rho. And this is the relationship. Again, this is a vector. It's a bunch of vectors added together. But this is the relationship that will allow you to compute these three guys. Now, the only problem is that at this point in the procedure, you do have these already expressed in LVLH, right? I have done it. That's how you do it. So this is already in the right basis. This one, no surprise, this is 0, 0, omega. We said that the chief is in constant circular orbit around the planet. And if I want to express the angular velocity of the LVLH with respect to E, we discussed this. In LVLH, that's what you get, 0, 0, omega. It's only a component. It's a rotation about the angular momentum vector. So these are the two guys. Again, think about you are integrating the equations of motion in ODE 45, and everything that is created at each time step is position and velocities in ECI. So these are probably expressed in ECI. What do? Well, you just take R again and multiply in front of this difference. So that after you do this, every vector on the right-hand side is expressed in the right basis. And you can add them together, and you are actually getting x dot, y dot, z dot. Makes some sense, makes no sense. Silence. Shall I show you in MATLAB? Yes.
So when you do R times the difference of velocities, you're getting the velocity in LVLH?
Yes. It's a vector. Each of the two mass points have their own velocities seen by the inertial observer. It's the same vector, it's just that I'm projected in a different basis.
Okay, and then you just have to subtract the rotation.
And then I have to subtract this term, which is due to the fact that the LVLH basis is not fixed, it's rotating. Yes?
So that R times that will give you...
It will just take this, which is probably a vector that it's expressed in a basis which is not this one. It will just take it and move it to that basis. Exactly the same thing that I've done here. So I could basically write exactly the same expression where the parallel would be this. Well, I don't know what to write here. Well, here would be VDX E minus VCX E, etc. They become, that difference becomes VDX in LVLH now minus VCX in LVLH, etc. It's just taking a vector, projecting it somewhere else. Any other questions? Yes?
So you bubbled around something that had a super strict speed, and you just multiplied it by R, and then on how you're able to just multiply those two terms by R.
This, how am I able to multiply this?
Yes, because the superscripts are the same for each. So is the R...
Oh, no. Remember, well, I don't know if you remember, but I may have said at the beginning, I hope I did, that when I take the rate of change of a vector in a certain frame, the left superscript it means the frame where that vector has been, the rate of change has been computed. So basically, VD in E is just indicating that this is the rate of change of the radius of the deputy, and this rate of change is taken by the E observer. So I think the difference is this superscript here indicates that this is a vector that has been originated by taking a time derivative, and you need to specify when you take the time derivative of vector who has done that, because it depends on the observer, right? While when I put the superscript here, the subscript here on these guys, I'm just saying that I am expressing a vector in a certain basis. Does it make sense?
That wasn't, I guess, exactly my question. I guess my question is, in the top you had just VD minus VC, and then you pointed down, and you have R times VD.
Oh yeah, because this is already, because these other, okay, I should probably write another equal and see and show how the whole thing looks like, right? So this is also equal, because this is, let me see. I think this, yeah, there is something that is to be specified here. So this equation as it is, it's perfectly fine. It's a vector equal to another vector, right? It doesn't, this is a vector, this is another vector. The fact that this is expressed in a basis that's expressed in other basis, it's okay. It's not a problem. But now, what if you want to take and actually tell me what these guys are? You can't do it unless all the vectors are expressed in the same basis, right? Make sense? Okay. So to express everything on this side on the same basis, I have to take the VDE corresponds to what? VDE will be some VDX, VDY. It's a three component vector, right? If you think about MATLAB, it will be three numbers, right? Like this. This is expressed in ECI. I have to express it in this basis to be able to go component by component and equate them. No? Yes? Maybe?
Just saying why aren't VD and VC superscript? Why isn't there LVLH instead? Because everything else is in the LVLH.
Why aren't these in LVLH? Oh, D and C just means deputy and chief, by the way. It doesn't, yeah. The E?
That's with respect to, did you change? Okay, so R is just the conversion factor.
Yes, but let me take one step backwards. This is an important point. So, if you have a vector, say that you have a reference frame A and a reference frame B, right? These are reference frames. And that's exactly what we have. We have a reference frame LVLH and a reference frame ECI. Make sense? Transport theorem tells me that if I take a vector, call it B, if I take the rate of change of B in, doesn't matter, in A is equal to the rate of change of B in B plus the omega of B with respect to A cross with B. Okay, that's what the relationship that I have right there. The left-hand side would be the rate of change of B in some A, that in my case is L. The right-hand side, well, it was the other way, I'm sorry. This piece will be the rate of change in A. This piece is this guy, and that omega, I moved it to the other side, is this cross product. The weird thing is that there are two vectors involved here. I started with RD minus RC. That's why it looks a little different, but that's really what it is. This is the rate of change of the difference of the positions of the two satellites taken in some A reference frame. This is the same thing done in some B reference frame, and this is the cross product that it's there because of the transport theorem. Yes?
So is the whole side of that equation the R times the velocity?
No. Only this. So if, as we have done so far, when you integrate, for example, in ODE 45, I'll show you exactly this example, but if you integrate in ODE 45, MATLAB creates, at each single time, creates three numbers that are the position of your satellite, right? And three other numbers that are the velocity of your satellite, right? They're numbers. So, I don't know, these may be 7 kilometers per second, 0, 0. It gives you this thing, right? Now that's, you need to know in which basis is expressed. Because it's a vector, you can call this a vector if you know what is the basis, otherwise they're just three numbers. But we do know what the basis is, right? We know it's ECI. So when I put together this equation, I will probably have these two vectors in ECI. That's what we have done so far. And I don't like that. If I need to find the components of this is a vector equation, A equals B. But when you have a vector equation, you need to make sure that both sides are expressed in the same basis. Otherwise, I can't come up with an equation x dot equals something. I cannot do it if they're not in the same, all of them are in the same basis. So this is just doing exactly what I was doing right here. I'm taking a vector, it's not the capital X, capital Y, capital Z, it's this one, it's the difference of the velocities. I can call it with just one name, I don't know, B, C, whatever. This is a vector, right? And I don't like in which basis it's expressed, so I move it to LVLH. I project it into LVLH. Still not clear? I can do it again, try to explain it a different way. Let's try. Okay. This is my raw vector. And I said it's defined as RD minus RC. I hope we agree that I can write this. Rate of change of raw in ECI is the rate of change of raw in LVLH plus the angular velocity of LVLH with respect to ECI crossed with raw. We agree on this? Forget what raw is. It's just a vector. A random vector, this doesn't even exist. For any vector that I can give you, if I have two observers involved, I can always write the transport theorem. This is the very generic expression that I have, right? Yes?
So just to be clear,
yeah.
The left side is in ECI,
yeah.
and the right side is in LVLH.
This is in LVLH. This is in ECI.
Okay.
This plus this is in ECI. That's what the equation is telling me. Yeah. These two guys are not the same unless they are the same frame. Because the two observers see something different. And the difference is this piece. Is the fact that one of the two is rotating. Or both are rotating with respect to each other. It doesn't matter. So all I have done there is this one. I just called it x.il, y.il, z.kl, right? That's what I've done. And this one has become, because this is what it is the rate of change of RD minus the rate of change of RC, both with respect to E, still equal to the same thing, right? Plus omega LE cross with rho. Now, as long as you remain, symbolic like this, you don't have to implement this in MATLAB in any program, or you don't have to do it manually. You don't actually have to have numbers here. This is all fine, okay? This is a perfect, legit vector equation. But the moment you want to go component by component, because this corresponds to three equations, right? These are vectors, so this corresponds to three equations. I can't say, I need to make sure that, again, they are expressed in the same basis. You always have to do that if you equate two vectors component by component. And so all I've done is, I know this is what I'm looking for. This is my unknown. So I decide that I write it this way. I decide that I want this vector to be projected in LVLH, because that's what I want, right? K, L. And I want, so at this point, I want everything else to be in that basis. Probably this will not be. This whole thing is not going to be. But again, call these just, I don't know how to call it. What do we want to call it? What do you want to use? Some big V vector, it's the difference of the velocities. Well, if it's not expressed, if it's not projected in ECI, you have to project it there. The same way I've done that operation with big X, big Y, big Z. Right? So this V will be given, when you do it, when you actually implement these in MATLAB, will be given by three numbers. These three numbers are not corresponding to the basis in LVLH, so you have to multiply that times r. It will give you the corresponding projection in LVLH. The other guys will probably be already in LVLH, because this row, I have done it there. As soon as I do that operation, I have this vector expressed in LVLH. This, I told you what it is in LVLH. Is basically, it's just omega k of LVLH. Make sense? No? I think it will make more sense in MATLAB, probably. This is to get to implementing this, to numerically solve it, to do it in some kind of software. Because again, these are just vector equations. The moment I start projecting them, when I have to implement in some kind of code, I have to make sure I'm talking the same basis, because I can't equate two things that are expressed in different bases. Okay? Let me see if this clarifies more. So I'm going to redo this exactly the same steps in MATLAB. And this file I have here is the uncollected homework 9. It's exactly what I was asking you. If it starts. Okay. So go read that homework. Actually, I can probably pull it up. Teaching. So I'm giving you two satellites, chief and deputy. Of course, the chief has to be in circular orbit, because that's what we have assumed. So the eccentricity is 0. The deputy in this case is not, but you can play with this as a slight eccentricity, and notice that the same major axes are different, but that's just an example. You can change those numbers, and if you have time, I'll play with different combinations. So what I'm asking you to do is this. Take these orbital parameters, convert them into r and v state vector. You've done that before. And then integrate in Cartesian coordinates the motions, the two trajectories, with a time step of 1 second. I just change that and do it for 10 hours. And then there are two ways that you can represent that vector rho and its rate of change. One is compute the initial conditions, so do these operations that we have discussed just once at the beginning, and compute x0, y0, z0, and x dot 0, etc., and use them in Closey-Wilshire, which is 0.2. Or you just do these operations that we discussed at every single time step. It doesn't give you linear equations that you can use. It gives you the actual real non-linear relative motion. It tells you how the position of the two changes with time projected in LVLH without approximating, without linearizing. So the steps that I have described here, if you do it at each time step, say at each time step you have position of chief, deputy, velocity of chief and deputy, you do this, you get x, y, z, x dot, y dot, z dot, but they are not given by the Closey-Wilshire equations. There's no linearization, I don't use them, right? So, let's see. This is what I'm doing. The chief is here. I convert into a position and velocity. The deputy is here. I convert into position and velocity. That's no surprise. And then I do two different integrations, right? In ODE 45. And remember that what I am creating here with these y out vectors is a bunch of positions and velocities in ECI. So each time step, that y out contains 6 numbers, and those 6 numbers are, for example, for the chief, it's r chief at a given time. It will be some x, capital X of the chief, y of the chief, z of the chief, capital X dot of the chief, y of the chief, and z dot of the chief. And this thing is in ECI. We've done this for a long time now. And then, so I can probably stop it here, because this is really the core. This is nothing new. It's going to take a while. I chose 1 second. I wanted to do fine numerical integration. This is summarizing everything that pretty much we have discussed. So, what do you do? This is the operation of ignoring Cauchy-Wilshire equations and computing how the chief sees the deputy, little x, little y, little z, at each time step, and how he sees it moving, x dot, y dot, and z dot. X, y, and z, x dot, y dot, z dot are what the chief sees. You're sitting on the ISS, the shuttle is approaching, that's what you're measuring, relative position and velocity, right? So, these are the steps that we discussed. You define the x direction, the I direction of the LVLH by taking the position vector of the chief, normalize it. What is this? It's another vector expressed in ECI. It's the first row of this matrix. A, B, C, E, F, G, H, I. That first instruction, line 115, is going to give you this. Okay? That's how it's set up. It's, that's one. Second one is D, E, F. And then G, H, and I. Now, I take the difference of the positions of the deputy and the chief. That is rho. If you don't do this in front of it, this is position of the deputy minus position of the chaser. That vector is expressed in ECI. That is rho expressed in ECI. But if I'm sitting on the space shuttle, I could not care less of rho expressed in ECI. I continuously move with respect to ECI, while LVLH does not move because it's defined based on my vector and my velocity. Make sense? Yes?
So just want to clarify,
yeah.
Sometimes when there's a subscript C, you say chaser, and sometimes...
Yeah, I know. Yeah. Okay, so there is, you'll find this in literature. Chief is also called target sometimes. And deputy is also called chaser. And so since I've used both of them, I see a C and sometimes I think chaser, but it's not. Yeah. I'm trying to stick with the book, which I think uses chief and deputy. Yeah, sorry. And so if you don't do anything, that's in ECI. If you pre-multiply, so this is your R matrix. I multiply, and that's giving me my rho vector. This is telling me how the chief sees the deputy, and it's telling me how this vector is projected in LVLH, right? This rho vector. That's what I'm computing at that step. The next one is the last operation that we have done. This is the difference of the velocities, this part here. Difference of velocity between deputy and chief. As it is, it will be in ECI. It's just another vector, right? It's in ECI though. It's projected in a basis that I don't like. I multiply times R. That takes the vector and projects it into LVLH. But that's not enough because the transport theorem, we know we need to subtract the cross product of omega. This 0, 0, 1 theta dot of the chief is that 0, 0 omega cross rho. And rho, I have already built it so that it's already in LVLH. So in MATLAB, you cannot add two vectors if you're not sure that they are in the same basis. MATLAB doesn't recognize basis. It takes three numbers and adds three numbers. It's up to you to make sure that these first three numbers and these second three numbers are projections of vectors in the same basis. If they're not, it will still give you something. It will be meaningless. So that's the difference between writing a vector equation on the board and implementing. Implementing a vector, when you implement it in MATLAB, a vector becomes three numbers. Right? And so if I do that, I do it for each time step. I create x, y, z, x dot, y dot, z dot without even using Cauchy-Wilshire equations. I can do that. But that requires me to integrate the equations of motion, and I forget about using the beauty of linear equations, but I can do that. And so I do it. I create, let me continue. What's going on? It's thinking a lot. Okay. I think the star, let's see, the star is the starting point. See, notice one thing, well, we'll talk about Cauchy-Wilshire in a second. So that is where they started from. This is how, okay, let's see, the chief is sitting right there, 0, 0. That is by definition where the chief is, because this is the relative plane, the plane xy of LVLH. And I have x this way and y that way. So in other words, you're going higher, the Earth is down here, that's the chief at 0, 0, and this is the direction of flight. Y positive. Well, the deputy just starts, with respect to the chief starts here and just does this motion and, you know, goes away. It's drifting away, right? It's actually going ahead or behind? It's going ahead. Why is it going ahead? What do you think is the relationship between the same major axis? See, the chief had the same major axis of 6, 7, 9, 0 something. The deputy has, did I say chaser again? Tell me if I do. The deputy had a couple of kilometers less. The period of the deputy is shorter than the period of the chief. It's going faster. It's going ahead. The oscillation is due to the fact that there is an eccentricity. Now I'm going to remove the eccentricity and show you that that goes away. But that's what you have to look at. That's what justifies why it's going that way. Now here, instead, what am I doing? I am taking that. I have computed a bunch of raw vectors and the corresponding velocity, relative velocities. I take the ones, only two of them, at initial time, and I use them as initial conditions for Cloyce-Wilshire equations. That's how you would do in reality. You know where the chief is, you know where the deputy is, and subtract the two and do all these projections. And integrate those equations, and I'm going to plot what I get from Cloyce-Wilshire equations on the same graph. And it's going to take a while. And here it is. The red one is what you get from Cloyce-Wilshire equations. They are very similar, right? But then you start going away. 60, 80, 100 kilometers. Is that still close proximity? You know, the linearization is still okay. That depends on you or what kind of maneuvers you're looking at, what kind of approximation you can live with. There is an error up there at the end of this simulation that is probably, I don't know, 500 meters, a kilometer. Can you live with that? Maybe. It depends on the application. But this clearly shows that linearization is fine up to a certain point. It's linearization. You're going away. The linearization point is 0, 0. And this is only the plane, by the way. I'm not showing you the z, because I think the plane is the fun one. The z is kind of annoying. It just goes up and down. But that's really what's happening. This shows how the linearization at some point breaks. Now, if I'm going to remove the eccentricity for the deputy, what do you expect to see? They are now two circular orbits. The chief is above, the deputy is a little below, a couple of kilometers. What do you think will happen? Still goes fast, right? But it will probably just be a line. There should be no oscillation. They are just, in real life, they are two circles. One is run a little faster than the other one. But this is what you have. Deputy is down here, and chief is up here. And now, remember that this is the point of view of the chief. He's looking at things from this axis. And this guy is, well, the y, I picked it this way in this case. This guy is going faster. So I should see an increasing, still an increasing y. Sorry, it's going faster on this line, right? But there will be a difference what you get from doing it without linearizing and doing it linearizing. In one case, you get a straight line, which is not popping up. And in the other case, you get something curved, which is what you should get. I should probably use that time step. That's okay. So yeah, that's okay. Top one. What did I say? The red was Cloyce-Wilshire, right? That's exactly linearization, right? You take something that is curved and you make it linear. From the point of view of the linearized equations, this object is just going straight. But that's not true, because this is really what it's doing. And so you see that in this case, the linearization is really terrible, because the real trajectory is actually going down pretty quickly. Well, but here we're talking about already a few kilometers. So they start separating pretty soon. And that's what you should expect. These are curved trajectories. They're not straight lines. You're not going in a straight line and someone else is going slower than you or faster than you in the same line, right? Yes?
So it only works with one being in circular orbit and the other being in orbit?
No. So what we have derived, the Cauchy-Wishart equations, they are fine for one of the two chosen as the reference being in a circular orbit, yes. If you want to try both not being in a circular orbit, there are other models that we're not going to see that you can use, more complicated models. You can still try to use them. They will break apart even worse than in this case.
So would this still be okay if you're like in a
It doesn't look like, well, again, it's up to you. How much error can you tolerate? Again, these are kilometers. So see, I have zoomed in, and I don't see I almost don't see any difference in the x, right? And here I'm talking about 200 meters, 250 meters. So that's pretty far, right? I mean, if you're thinking about doing rendezvous and docking, something that's 200 or 300 meters away, you probably don't even see it. Well, you probably see it, but it's still far. And I don't see a substantial difference between trajectories. I don't see anything on the y-axis. So usually what they say is what we say is a few kilometers is okay, but after that.
And that graph is just the physical location of the spacecraft moving.
That's the deputy, that is the trajectory of the deputy as seen by the other guy. Yep. I think we should stop. Okay. So this is what you should do. You should really do this.